In the previous video, we talked about tenses, all of this. Alright. However, I would like to build on indicial notation to make it a more defined and clearer notation definitions, and then we will carry on with the rest of the definitions of tenses. Alright. And nothing is best described other than using back these definitions of a 3D vector, alright, a three-dimensional vector where v is equals to v1, v2, and v3. Okay, so how do we do and start off with that giving a definitions of indicial notation? Okay, whatever. But anyway, so how do we start? We know that the indicial notation is based on looking at this one. Okay, how many are there? If you were to go back to the matrices, you know that indicial notation depends on how many numbers. Alright, if there's two numbers over here, 1 and 2, so you know this is two indicial stuff. Alright, so in this case, this is one indicial notation. Okay, so how do we use this one to define certain stuff? So we can actually make things more short form, okay, make things more efficient when writing the stuff, such that it's pretty much easier. And therefore v1, alright, these are the components. If you remember, these are the components, v1, v2, v3, and the basis vectors are the unit vectors, e1, e2, and e3, correct? And therefore, you can, since they are v1, e1, and v2, e2, you see that they have some similarities in there, right? And therefore we can summarize them and rewrite them as vi, alright? Write them as vi ei hat, alright? So if I is equals from, alright, from I is equals to 1 to 3, alright? That's the Einstein summation rule. And therefore, from when I is equals to 1, this is the 1, if it was 2, this is the, and 3, this is this. Alright, so we can summarize this equation in terms of these aspects. Alright, therefore what is I? Okay, what is I? Okay, in this section here, we know that this I belongs to the V. Alright, now what if it's U, the vector U in this case? I have u1, u2, and u3. Alright, and therefore in such of a case, then what we can do is that instead of, so v is some representation of I, correct? So we can represent u in terms of j. Therefore we can rewrite this u vector is a summation of j is equals to 1, okay, to 3, and instead of I write vj. My pen is not working very well these days, I don't know why. Okay, so in terms of j, and this is why, as I say, the relationship of u and v in the last video can be represented in terms of this matrix. Alright, we call this W matrix. Okay, and therefore we can simply write them in terms of ij. Right, so this matrix itself is represented by all these stuffs over here. Depends on what I values and j values you pick, and this is the thing that you often see in your books. Alright, wij. Alright, so this I depends on one vector, j is another vector. If it's k, then you're going to talk about the third vectors and things like that. So this indicial, we'll call this indicial notation, I, j, k, l, m, or whatever. It all specifies our number of vectors that is being somewhat go into these things, and it also defines the number of orders, if you remember, for the tenses definitions. So this is the number of orders, or the number of ranks, or the number of the indicial notation. Alright, and therefore this is a very powerful understanding, and therefore we can call this phenomenon, alright, this just draw in a different color, this where's my pen? Great. this whole thing, alright, in terms of I and j, alright, we can call this the free index, okay, because they're independent. They are in terms of some I and some j's, okay. Alright, so knowing this free index, let's start out with something different. Alright, let's copy this one and then I'll just paste it over here. Okay, we'll touch on the concept of dummy indices and how do we start off with dummy indices. I'll just rewrite them just as that, and this is the free indices that I said. Why free index? Because they're independent, I and j. Alright, so now let's derive something that is called the dummy index, alright, by using the concept of canonical delta. Alright, so canonical delta, I have something like that. Delta I j is equals to, so I have some intervals, alright, and therefore I have a canonical delta. This is the definitions of a canonical delta. Alright, it is a 2. Alright, I don't know what is it used for, but it is a 2. A 2 to help us determine certain stuffs. Alright, I'll not define it in a hard ways, but this is the definitions. So this 2 itself can help us change this one or this one into a dummy index. How? When I is equals to j, it is equals to 1. When I is not equals to j, it is equals to 0. And therefore, if we take a look, alright, so this is in terms of I and j, right? It's in terms of I and j. So it is, if I and j is equals to, it is the same, so this I and this j, alright, so they are both 1, so I and j is the same, and therefore we can keep this and we just write it as w11, we just keep it, alright, times 1, okay, 1 times, because, alright, and therefore if it's 1, 2, if I and j are different now, alright, then we can set it as 0, and therefore I have 0 over here, and since this is also not the same, I have 0, and in the end I'll achieve something like this, alright, where I'll only have the dummy indices left over, alright, where I have also the 1 times w22. So as you can see, they are all the same indices. I and j are the same, and I can rewrite this all this stuffs, alright, because if you were to sum it up, because these are all based on different vectors, so there's 3 vectors over here, right? 1, 2 and 3, if you were to look at it in this manner. And therefore, if you were to do that, what we have is that I will have w11, alright, plus another vector w22 plus another one w33. It may not be necessarily a vector, okay, I don't know what it is, but at least you know that I'm summing them up together as a matrices. So I'm summing this one into one directional, so one vector, and then this one summing up together, I have another vector, summing up together, I have another vector. Alright, so these are 3 vectors, I will assume, alright, I may be wrong. Alright, and therefore this is how I write this in terms of the directional vectors. And I also can rewrite this using the Einstein summations method from R1 to 3, because I have all this. These can be all represented by i's only now, right? And therefore I can just write them as t I. Alright? So if if I is equals to 1, then I can write in terms of w11, alright, and so on. Maybe I should write in terms of wii. Right. Okay. So if it's 1, then I'll just write 1, 1, 2, 2, and 3, 3. I hope this is pretty clear. So far we have used we have derived this one, right, the free indices, and then we apply the canonical delta, alright, we apply the canonical delta, and we achieved the dummy indices. Alright, this is one form. Okay, this is only one form. Now let's introduce you to another form. Okay, another form where, for example, now let's take a look in this one. this one, as you can see, this is what we have derived earlier, right? So it's in terms of the vector times the unit vector. So I can just summation them into this phenomenon, right? And therefore I can take these definitions, I paste it over here, okay? And then I take the matrix which we have just drawn over here, I paste it over here. If I were to multiply, okay, I were to multiply this vector, alright, this vector with this tensor, alright, this is the matrix, I call this a second order tensor now. If I were to multiply them, what would I have? We know that the unit vector, alright, the unit vector is a constant 1, alright. Therefore we can also rewrite them as vi, alright. We can rewrite this whole chunk as vi, that's all, alright. So in the end we will have v1, v2, v3, alright, and the summation from I is equals to 1 to 3, alright. It's the same thing to describe this and this, alright. I'm just doing this system right now. Okay, this may feel a bit boring, but I just want to prove certain stuff to you. And as you know, this vector is in terms of v1, v2, v3, and we can say that this is 3 times 1, row times column, right? So 3 rows times 1 column. And therefore we can take vi, alright, which we have derived earlier, plus, not plus, multiply with this tensor. Alright, as you can see, these are all the same, and we can call I as the dummy indices. Alright, we can call I as the dummy indices. If you have to remember back that how we achieve this matrix is to multiply, is a relationship between a vector u, alright, a vector u and a vector v. You had a vector u and a vector v, correct? Is the relationship between, and then u is in terms of j, v is in terms of I, alright, is in terms of I, as I say. So if I were to take another vector of I, multiply with already existence of I within this matrix, alright, so this is already comprises of u and v. So you are simply taking another v multiplied with another v. Alright, so in this sense you are saying like you are taking another similar vectors and multiply it in together. So in this sense they are in the same range, or in the same, I don't know whether can I call it domain or not, but it's that meaning. So they are actually in the same range by definitions, okay? And therefore this is 3 times 1, and we know that this is 3 times 3, and therefore we will have a 9 times 9 matrix. Oh, 9 times 9, 3 times 3 matrix, sorry. Okay, we have 9 values, okay? And therefore what we have over here, I'll just fill it up faster so I will save time. And therefore after writing down all this, alright, so v1, alright, if you remember the vector itself, alright, is v1, v2, and v3. Alright, so I'm simply multiplying with this so-called the matrix itself. Okay, and I'm just simply multiply them alright, into all this little stuffs over here. That's all. So, and then this v2 is multiplied into all this over here. Okay, hope this is clear. And therefore this is one form of a vector, this is another form of a vector, this is another form of a vector in 3D. So in 3D this is some vector, and then in another 3D this is like maybe another vector. In 3D, alright, this is maybe another vector also. Alright, if you were to define them in colors, this is one vector, and one vector. Okay, and therefore as you can see, v1, w1, v2, and then this, as you can see there is a trend going on. So I can actually sum this out. So I can say that this is in terms of the x-axis, vx, wx, and then this is, as you can see, this is 1, 2, and 3. the changing thing is in terms of the j that is changing. I is always the same, right? So therefore I can just simply write as j. Alright, or maybe I'll just write it as 1. Okay, I think I'll just write it as j. It'll be easier. And then if it's vy, wy, j. Alright, since this one is always the same, it's in terms of y-axis, right? It's in terms of the y-axis. So for example, this is x1. Maybe I should write it as x1, x2, and x3. So this is the x-axis, this is the y-axis, this is the z-axis. I'm simply writing them in terms of x, y, and z. Alright, so this is z, which is 3. Alright, which is this one. X3 is z, and therefore that's why I'm writing over here. And if you were to write in terms of the summation of the directions of the vectors, I'll just simply sum them out. Alright, I'll just simply sum them out together. Okay, where's my pen? Okay, it's over here. And therefore this whole chunk describes this all the stuff over here. Okay, this is a bit, yeah, and therefore this is equals to vi w ij. Alright, where I can be x, y, and z in this case. Okay, I hope this is pretty clear. Alright, I may be wrong in because following my text itself something is different. Alright, but this is somewhat the meaning of it. Alright, and therefore this new form, okay, I can simply say that this is equals to I will just say that cj. Alright, so this I, this dummy indices can be somewhat removed, and the only variables that is changing is in terms of c and is in terms of j itself, as you can see from this diagram itself. 1, 2, and 3 is changing, while the v and w, they are all the same throughout the whole section. Alright, and the only thing that I want to just to convey before I end this is that why am I saying that I'm wrong is because of this multiplications over here. Alright, this may be transposed. Alright, but I don't know why the definitions in my book itself didn't write any transpose at all. Alright, but the general concept, I would say that if I were to take this, then I'm simply taking this as a scalar vector, somewhat a scalar magnitude onto this so-called components, I would say. So this one as a scalar on this component, and then this as a scalar on this component. I don't know, this might be the meaning, but in any case we have derived this one. Alright, so this one is absolutely correct, alright, in terms of j. Just that the derivation part of this I may be wrong. Alright, so this video is kind of long, so I'll just not drag it too much, and we have just cleared away only this part. So I think that next video I'll just do out this part. In fact, this video we also talk about free index and dummy index. Alright, because in terms of the how things goes, I believe that this is better, and therefore next video we'll talk about this, and I'll see you there.